Hello everyone, and welcome back to this series on real analysis. Today we're going to be discussing a very important method for approximating and representing functions known as a Fourier series. So what exactly is a Fourier series? Well, from the Weierstrass approximation theorem, we know that we can approximate a continuous function up to any degree of accuracy for which we desire with a polynomial. In particular, power series, which we already know several theoretical things about. In particular, a power series representation for a function f of x is one of the form, the sum from k is equal to 0 to infinity, of ak times x minus, let's call it c. So c is called the center of that power series, to the power of k, and ak are the power series coefficients that pretty much are dependent on the function f for which you approximate. So if we have a special formula for these coefficients, in particular Taylor series, then we can pretty much find a nice representation for a power series. So a Taylor series is a special form of a power series. So pretty much what is this? Well, this is the sum from k is equal to 0 to infinity of the kth derivative evaluated at the center of that power series divided by k factorial times x minus c to the power of k. So pretty much the connection between power series and Taylor series is just a special representation for ak, where ak is the kth derivative evaluated at the center divided by k factorial. Now, power series is not the only representations for functions that exist. There are actually several famous ones, but another one aside from power series, which is just a polynomial in disguise, at least an infinite degree one, is what we refer to as a trigonometric series. Now, what exactly is a trigonometric series? Well, a trigonometric series is a representation of some function f, but in terms of polynomials, it's going to be a linear combinations of sines and cosines. So it's going to be the sum from k is equal to 0 to infinity of ak times the cosine of kx plus bk times the sine of kx. Right? So trigonometric series is sines and cosines for your basis functions, for your functions in R2, or moreover R in terms of its range, and power series uses polynomials as the basis functions for their functions there. So, at least from the single variable calculus perspective, one can show very easily that the coefficients for a Fourier series are equal to, so a0 and b0 are special for this Fourier series. So a0 is 1 over 2 pi times the integral from minus pi to pi of f of x dx, and b of 0 is equal to 0. ak is equal to 1 divided by pi times the integral from minus pi to pi of f of x times the cosine of kx dx, and this is for k is greater than or equal to 1, and the coefficients bk, right, because we have sines and cosines, so bk will be pretty much the same thing as ak, so integral from minus pi to pi of f of x times the sine of x kx dx. And again, this is true for k is greater than or equal to 1. And this is for functions f that are supported on the interval minus pi to pi to r. Now, generally speaking, you can extend this domain to minus L to L to r just via linear transformations of the domain. But we're just going to be keeping the math on minus pi to pi, and then you can extend it if you desire. And also, if you do not know where these coefficients come from, I do prove this in my single variable calculus series, which I guess you could view as a prerequisite for this particular Fourier series video, where we're going to get just a little bit more detail out of what Fourier series are and when they exist. So one of the exercises that I usually recommend for beginner Fourier series people using these formulas. So if we have the function f of x is equal to the absolute value of x for x in the interval minus pi to pi, if you were to take c to be equal to 0, then we clearly already know from basic calculus that this function is not differentiable at 0, meaning that the Taylor series, t of x, does not exist, right? Because the function needs to be differentiable at that point, in particular infinitely many times differentiable, in order for you to find those coefficients. But just because it's not differentiable there doesn't necessarily mean it doesn't have Fourier series, and in fact, the absolute value of x does have a Fourier series on any closed or open interval. In particular, I leave it for you to show that f of x's Fourier series representation is equal to pi over 2. So that's your a0, and then minus 4 divided by pi times the sum from k is equal to 0 to infinity of the cosine of 2k plus 1 x divided by 2k plus 1, the quantity squared. Right? That's a fun little exercise, and it's just as an exercise for those little integral representations for AK, BK, A0, and B0. But nonetheless, it is an existing Fourier series, and it definitely does converge to the absolute value of x, at least on the interval minus pi to pi. So what exactly are we looking at here? So the absolute value of x has this representation. Right, so this is positive pi, and this is minus pi. So this is the only part of the function that the Fourier series is associated with, and it does exist outside of this interval, but it is going to be periodic in terms of what it represents on the interval minus pi to pi. Right, so this piece right here, right, this is the only part that we're really concerned with, and obviously if you want to extend this, you can just stretch this out to get a more wider representation for the absolute value of x. Right, so that's pretty interesting. So now that we have the Fourier series, let's talk a couple theoretical things about them. Let's define t and x to be equal to the partial sum of the Taylor series for a function. That is the sum from k is equal to 0 to positive n, and here we have the Taylor coefficients times x minus c to the power of k. For this to exist and converge to a function, we need two things. The first obviously is differentiability. We need the kth derivative of f evaluated at c to exist for all k from 0 to n, and also for it to converge, we also need it true for n plus 1, n plus 2, all the way up to infinity. That is, it needs to be infinitely many times differentiable. Also, we need convergence. That is, this t and x needs to converge to f of x. That is, the difference between them needs to converge to 0. Right? So these two things need to exist for that Taylor series to exist. Now, if f does have a Taylor series at x equals z, we can show that for some L greater than 0, f has a Fourier series approximation on c minus L to c plus L. If you want to pause this video to see if you can try and prove this on your own, feel free to do so. So how are we going to prove this? Well, we're going to make one simplification here for our proof. In particular, without loss of generality, what I want to do, I want to take c to be equal to 0 and L to be equal to pi. And you can easily do this via linear transformations, transforms on the domain of our function f. Right? So once you do this, then a lot of things have become a lot simpler. So what do we know? So since our f has a Taylor series at x equals 0, this means that both differentiability and the convergence criteria for that function f satisfies. So since we have that f is differentiable, then we also have f is also continuous. In particular, it's continuous on some open interval. Let's call it n epsilon of 0, containing 0. So that's your little open interval, 0 minus epsilon and 0 plus epsilon. And hence is Riemann integrable on minus epsilon to epsilon, for which I'm going to define from here on as the interval I. Right? So we can clearly say, or in a more compact form, f belongs to the set of Riemann integrable functions on interval I. Now let's define a couple more functions. Also, if we have this function gsk of x, for which I will define as the sine of kx, then we should be able to prove that gsk is also Riemann integrable on I. right? Because that's just a sine function. Sine functions are continuous and hence Riemann integral on R more over on I. Also, if we define another function, gckx, which is going to be defined to be equal to the cosine of kx, then you should also be able to see that gckx, or gck, is also Riemann integrable on I. Right, so we have several Riemann integrable functions. We have f is Riemann integrable, gsk, and gck. Now you might be thinking, what's so special about these gck and gsk functions? Well, those are going to give us the Fourier coefficients for our Taylor series. So therefore, since f and g, both of these g's, belong to our Riemann integrable functions on I, then we know that the product of these functions, f times g, also belongs to the set of Riemann integrable functions on I. So since we have that, that means ak, which keep in mind is just going to be equal to 1 divided by pi, divided by the integral from minus pi to pi, of our f of x times the cosine of kx dx, this thing belongs to the set of reals, and also bk, which is equal to 1 over pi, times the integral from minus pi to pi of f of x times the sine of kx dx, also belongs to the set of real numbers as well. And why is that? Well, this function and that function, that function and that function are Riemann integrable on I, therefore that integral exists and is finite. So now that we have these objects existing, which are the Fourier coefficients, that means what? And they exist for all k in 0, 1, 2, all the way down to n. So therefore, if we define fnx to be equal to the Fourier approximation, the sum from k is equal to 0 to n, of ak cosine of kx plus bk times the sine of kx, and I believe I should have swapped these around. So there's cosine and that's sine. Then this object, because ak is real, cosine is real, bk is real, sine is real, and the sum of a bunch of real numbers is real due to closure, this is a real number and exists for all n in n, right? Because this is just the Fourier approximation to f on minus pi to pi, which is generally a specific case of c minus l to c plus l. Now, does this mean that this series converges to f just because the Fourier approximation exists? Take a moment and think about it, because that's the next question I want to address. So does the existence of Taylor approximations and Fourier approximations imply that Taylor approximations converge to the function f? Moreover, does the Fourier approximation also guarantee to converge to that function f? The answer is, take a guess, no. So let's first off recall a special case or counterexample for the Taylor series convergence issue. So the function that I want to work with to demonstrate this, let f of x be equal to e to the minus 1 over x squared for x not equal to 0, and define it to be equal to 0 for x is equal to 0. In case you're not familiar with what this function looks like, it does have a horizontal asymptote at y is equal to 1, and it kind of looks like a bowl. And it's kind of flat down here, and then up here, and obviously we're closing in that circle at x is equal to 0. So it does have a limit at x is equal to 0, and it is equal to 0, so it's a removable discontinuity. So you might be thinking, well, what is the derivative at x is equal to 0? Well, the derivative at x equals 0 is that particular object, and the limit is equal to 0, so the derivative's limit also will be equal to 0. That's not super hard to show. So that means the kth derivative of at 0 is equal to 0, and that's going to be true for all k in the set of naturals, including 0. So that means the Taylor approximation to this curve at x is equal to 0 would be equal to the sum from k is equal to 0 to n of 0 divided by k factorial times x minus 0 to the power of k, which is always equal to 0 for all k. All right, so that's kind of boring, I guess. So does this function converge to the original function? That should be an obvious no. So let's just formally state that. So if we take the limit as n goes to infinity of t n x minus f of x, that's just going to be equal to what? Well, that's the limit as n goes to infinity of 0 minus the function, which is just going to be equal to the function e to the 1 over x squared. Notice that that does not have n in it, so that's just going to be equal to e to the minus 1 over x squared, which is obviously not identically equal to 0 on any interval minus L to L for L greater than 0. So therefore, this Taylor series, even though it exists in terms of approximations, does not converge to our particular function. Now let us turn to the Fourier approximations and see whether they are guaranteed to converge. So what I want to do is consider the function f of x is equal to 1 for x greater than 0 and 0 for x less than or equal to 0. And I want to choose, without loss of generality, the open interval minus pi to pi, since that's usually easier to work with in terms of the Fourier coefficients. If you want to pause this video and see if you can find this Fourier series on your own, feel free to do so. So we need to find the Fourier approximation to this particular function and then see whether it converges to this function f. So the first thing that I want to do is find our basic coefficients, so a0. So a0 will be equal to 1 over 2 pi times the integral from minus pi to pi of f of x dx, but keep in mind it's equal to 0 everywhere from minus pi to 0, so we need not consider that portion of the interval. So this will just be equal to 1 divided by 2 pi times the integral from 0 to pi of the function defined on that integral, which takes the value of 1 everywhere for x greater than 0. So we know the integral from 0 to pi of 1, that's just going to be equal to pi, so we have pi divided by 2 pi, which is just going to be equal to 1/2. So that's what a0 is going to be equal to, and also recall that b0 is always going to be equal to 0 for the standard Fourier coefficients. Now let us figure out what for k greater than or equal to 1 these Fourier coefficients are going to be equal to. So let's start off with ak. So ak is going to be equal to 1 divided by pi times the integral from minus pi to pi of, what do we get? So that's going to be cosine of ks times our function f of x, and that's going to be equal to what? So we're going to be doing the same exact simplification. We're just going to integrate from 0 to pi of the cosine of kx dx, and that's going to be equal to what? So antiderivative of cosine is going to be sine, and we need to divide by that k by chain rule. So k is greater than 1, so we're not dividing by 0 here, so we don't need to worry about that. So we have the sine of kx, and then x is going to be evaluated at pi, and then x is going to be evaluated at 0. Keep in mind, sine of pi, or any multiple of pi, is going to be equal to 0, and sine of 0 will also be equal to 0. So this in turn entirely vanishes. So we have that ak is going to be equal to 0 for all k greater than or equal to 1, but keep in mind that a0 is equal to 1/2, right? So our ak coefficients will completely vanish. Now let's turn our attention to bk. So bk, again, is going to be equal to 1 divided by pi. Let's just simplify this. So 0 to pi of sine of kx times 1 dx, which will just be equal to minus 1 over kx times the cosine of kx. And then we need to evaluate this at pi, and then evaluate this as 0, and then subtract. So that's going to be equal to what? So we're going to have minus 1 over kx times, that's going to be cosine of k pi minus cosine of 0 times k, which is going to be equal to 1. And that's going to be equal to what? So let's just distribute this in and reverse the order. So that's going to be equal to, what is that? 1 over, and let's also not forget our lonely little term here. So let's see. Oh, that didn't have x in it, so let's not worry about that. So k pi. There we go. I had x there, and it wasn't supposed to be. So that's going to be equal to what? So that's going to be 1 over k pi minus cosine of k pi divided by k pi. And we can actually just simplify that to be 1 over k pi times 1 minus cosine of k pi. Right, so those are our coefficients, bk. Now, you should remember what cosine of k pi is because it alternates, because k is an integer, 1 minus 1, 1 minus 1, 1 minus 1. So this is going to be equal to, we can define this piecewisely, as 1 over k pi times 1 minus negative 1 to the power of k, which we know is going to be equal to 0 if k is even, and 2 over k pi, because 1 minus negative 1 is 2 over k pi, and that's going to be true for k. So those are coefficients, bk. Now that we have all of our ak's and bk's from k is equal to 0 to infinity, now we have our Fourier approximation. So we have that fnx will be equal to a0, which is 1/2, and then plus the sum from k is equal to 1 to infinity, keep in mind, ak is 0, so we're just left with our bk sine kx terms. So let's just plug in our bk values, which is going to be the following. So we're going to have the sum from k is equal to 1 to infinity. Actually, let's just expand it, and keep in mind the even terms are gone, so we're just going to have like sine 1x, sine 3x, sine 5x, and so on. So this is going to be equal to 2 over pi, so 2 over 1 pi times the sine of 1x, and then 2 over 3 pi times the sine of 3x, and then 2 over 5 pi times the sine of 5x, and this is going to continue all the way out to the last term, and keep in mind this is a finite sum, not an infinite sum. So let's actually get rid of that infinity because we do not necessarily know it converges yet. So our Fourier series approximation, which I define as follows, now that we have a nice representation for it, will be 1 over 2 plus 2 over pi factored out of the sum from k is equal to 0 to n of the sine of 2k plus 1 x all over 2k plus 1. So it has a very similar representation, similar to the absolute value, because it has that sine 2k plus 1x thing, but we have 2k plus 1 instead of 2k plus 1 squared. Right? So we have this particular object, and if you were to look at it for some finite value of n, what you'll actually see is actually something very interesting looking. Right? So here's our y is equal to 1. And what you'll actually see is it does try to approximate this curve. It has a little bit of wiggles, and then it jumps up, and then it wiggles over here, right? And then obviously it's going to, go back down and try and wiggle here, and then it's going to go back up here and try to wiggle here, right? And that's going to be on minus pi to pi. So now that we have our Fourier approximation, does this converge to the actual function as n goes to infinity? So one thing that we should see is that the Fourier approximation evaluated as 0 will be equal to 1/2 plus 2 over pi times the sum from k is equal to 0 to m, 0 divided by 2k plus 1, which is just equal to 1/2. And keep in mind, this is going to be true for all n, in particular as n goes to infinity. And keep in mind, our function was not equal to 1/2 at x is equal to 0. But this is actually an easy fix. Right? So this is an easy fix for us, because now we can just actually redefine our function, f of x. So we can say that, okay, f of x is equal to 1 for x greater than 0, 1/2 for x is equal to 0, and 0 for x less than 0. All right, we fixed that particular issue, so that's not really a contradiction that it didn't converge. Now, it is a contradiction for our original function, but our redefined function doesn't have this as a counterexample because it's definitely too easy to find. But another thing that you should be able to see, right, and this is an exercise for you, if you evaluate at plus or minus pi for this function, this also is equal to 1/2. Right, now think about that for a moment. So our function needs to be 0 here. It needs to be 1 here, right? So far we believe that it's going to approximate pretty well here. It's going to approximate pretty well here. It's going to pass through at 1/2 at x is equal to 0. But it has to pass through 1/2 at x is equal to minus pi, and it has to pass through positive 1/2 at x is equal to pi. And is that allowed? But keep in mind it has to approximate on the interval 0 to pi and minus pi to 0. It has to be identically equal to 1 on the right and identically equal to 0 on the left. Is that possible if it's guaranteed to pass through x is equal to y is equal to 1/2 at the boundary points? The answer should be no. Because if we view this at a little closer of an angle, right? So this is going to be our minus pi. This has to jump from 1/2 down to 0. So there exists some epsilonal distance such that it is not equal to 0 on the left, and same argument can be said on the right. And what can make us so guaranteed that this epsilon does exist? Because our function, our f function, right? Because keep in mind, fn, our Fourier approximation, is continuous on the interval minus pi to minus pi plus epsilon, and it's also continuous on pi minus epsilon to pi. Right? So since it has to go from 0 to 1, there's going to be some gap for which it's not equal to 0. Right? So that means there exists some x in between minus pi to pi plus epsilon such that fn of x is not equal to 0, and there also exists an x in the interval pi minus epsilon to pi such that fn of x does not equal to 1. So since it cannot be equal to those functions as n goes to infinity, then we clearly see that f of n of x does not converge to our function, right? So just because our Fourier series approximation does exist does not necessarily mean that our function Fourier approximation converges to our function of interest. So I know what you might be thinking. Are there any theorems that guarantee the convergence of a Fourier approximation to the actual function for which it approximates? The answer is obviously yes. The first theorem that I want to introduce is associated to Holder continuity. So recall that f is Holder continuous if for all a and b inside of the function's domain, there exists a non-negative constant k, a positive constant alpha, such that f of a minus f of b's distance is arbitrarily close to a minus b with respect to this particular relation given here. And you might remember that if alpha is equal to 1, then we say that this function f is Lipschitz continuous. Right? So Lipschitz continuity, a special case of Holder continuity. So the very first theorem associated to Fourier series that I want to mention, I'll call this theorem A, says the following. So if f is Holder continuous of any alpha level, then the Fourier approximation converges to f uniformly, moreover. So not just pointwisely, but uniformly. The next theorem that I want to introduce, this is useful for those of you who love infinite series analysis, says the following. So if f is continuous on the interval of interest, and also for this is on I. So if f is continuous and the sum of the absolute value of ak is finite, and the sum of the absolute value of bk is finite, that is, these Fourier coefficients are absolutely summable, then again, fn converges to f uniformly. Now notice that f Holder continuity is obviously a little bit more stricter than continuity. So f continuous is a weaker form of theorem A, but what if you do not have a function that's continuous at all? Because we obviously know that a function that is discontinuous still can have a Fourier series. So this is where the next theorem can be applied, and sometimes this theorem is referred to as the Dirichlet-Denny theorem, and it says the following. This one is a little bit more complex to state. So let's assume that f is Riemann integrable on I, right? So it's a little bit more weaker than continuity, because if it's continuous, it's Riemann integrable, but not the other way around. And let's assume that the integral over I of f of a plus epsilon plus f of a minus epsilon minus 2L, absolute value, d epsilon over epsilon, and let's assume that this definite integral is finite, then fn of a will converge to L. And obviously you need to ask yourself, is this equal to f of a? Yes or no. But this Dirichlet-Denny condition, or Dirichlet-Denny theorem, can be used to assess whether this Fourier series converges pointwisely to a point, more so pointwisely on an entire interval. So let's just do a brief example to show how a Fourier series does exist and whose Fourier approximation does converge to the Fourier series, even if we do not exactly know what that Fourier series is. So let's just take a nice little example. Let's assume that f of x is equal to x squared on minus L to L. Then the Fourier approximation exists and converges uniformly to f. So you might want to pause this video and see if you can prove this on your own. All right, so proof. So f has a Taylor series on minus L to L. We've already proven that polynomials have Taylor series. In particular, the Taylor series and the polynomial are the same on minus L to L, moreover so on R. Therefore, since it has a Taylor series, that means the Fourier approximation also exists by that theorem that I proved earlier. So let's assume that a and b are numbers from minus L to L. Then what do we know about a squared minus b squared? So f of a minus f of b. Well, this is obviously going to be equal to the absolute value of a plus b times the absolute value of a minus b. And since a and b are both between minus L and L, that means the sum of them is bounded above by 2L. So that means this is going to be less than or equal to 2L. And keep in mind, L is going to be a positive number, so 2L will be a positive number as well. So we're going to have 2L times the absolute value of a minus b, and there's actually an invisible 1 here. So that means that f is Holder continuous on I, Holder continuous of order 1, moreover it's Lipschitz continuous on I. So therefore, by that first theorem, we have that the Fourier approximation that is guaranteed to exist above converges uniformly to f on I. Right? So it's actually not super hard to prove that a Fourier approximation, if it exists, does converge to f. Right? So now let's come back to this particular function. In particular, let g of x be equal to 1 for x greater than 0, 1/2 for x equal to 0, and 0 for x less than 0. So obviously it's not continuous, and moreover it's not Holder or Lipschitz continuous either, right? So theorem A and theorem B definitely do not hold here. So what I want you to do on your own is to explore theorem C and how it can be used, i.e. the Dirichlet-Denny condition, and explore G of, let's say, I recommend, and let's assume that this is defined on minus pi to pi, and let's actually do closed interval here. And what I want you to do is explore G of 0, G of minus pi, G of pi, G of 1, and G of minus 1 to see if the Fourier series converge to the values for which they are supposed to converge to. And moreover, I want you to test G minus pi plus epsilon and G of pi minus epsilon, where epsilon is a small, arbitrarily small, but positive number. And again, recall what the issue is for this function. It has some issues near those boundary points, right? In particular, every time it has a jump discontinuity, right? Because it wiggles, and then it goes up, and then it wiggles again. So keep in mind, even if epsilon is arbitrarily small, this gap here always is going to exist, right? And some people refer to this as the Gibbs phenomena. So it's the Gibbs phenomena of Fourier series. So this is just some theoretical things associated to Fourier series that you definitely should know. There are several other things which we'll get back to later on, but I hope you enjoyed this Fourier series real analysis exploration of this very important and, to me, very interesting topic as well. I'll see you in the next video. Take care.